Hey everyone, hope you enjoyed the break. How are you enjoying Rails World? Great, thanks. So as we already heard, I'm Miles. I'm a staff engineer on Intercom's data stores team. Data stores at Intercom is an interesting team. We actually own our Rails deployment, caching, databases, lots of different things. You can think of it more like our core technologies team. Today we're going to be talking about a project I worked on last year called Guardrails, and as the subtitle says, we're keeping data separate in a multi-tenant system. So, what does that mean, and what are we going to say? Okay, first thing I'll let you know is this is going to be how we solved the problem we were having at Intercom, and more specifically, how we retrofitted it onto a 12-year-old Rails code base with nearly 2 million lines of code. And how we did all of that while causing the least disruption possible for all of our engineers. All of that is to say that your mileage may vary. This isn't going to be a recipe that will necessarily apply directly. It's something you're just going to have to digest and think about. Just some extra background. What is Intercom? We launched in 2011. We have the mission to make internet business personal. Our customers can use Intercom Messenger to chat with their customers on their website. We've been built on Rails since day one. And over time, we've diverged from standard Rails, sometimes more than others, but in recent years, we've been kind of up to date. So we're running on Rails 7. I hear Eugene is working on Rails 7.1 right now. So anyway, if you want to hear more about the Intercom and history and how we got here, you can check out my colleague Brian's talk tomorrow, which I believe is at 15:45. The other thing, the term we should define before we continue on, what do I mean by multi-tenant? That was part of the title of the talk. Just put simply, if we've got two customers, customer A and customer B, even though logically all of their data might be separate, it's going to be living together in one database, so shared infrastructure is serving all of the requests. So yeah, just keep that in mind. And what is the problem we've been having, and what are we trying to solve? Our data model at Intercom had grown pretty complex over 12 years of development. For context, we have almost 800 active record models. We have a big team of engineers working on a lot of separate or somehow interconnected features, and we want all of those engineers to be able to move as fast as possible. But moving fast in a complex environment always increases the risk of mistakes slipping through. Linting and specs can only do so much. Specs in particular are often only as good as the author's mental model. So what do those mistakes creeping in look like? What's wrong with this code? So we have addressable URI, and we're parsing a referrer, and then we're looking up an active record model called help center site by custom domain using uri.host. So that seems pretty innocuous. Or in this code, where we're looking up from rails.cache, something using conversation.id. So maybe from context, we can assume that's an active record model, and sticking the string parts on the end. So again, it doesn't look too bad. So taking that first example again, the referrer here was sometimes about blank. And I don't know if you knew this, I certainly didn't, that if you ask addressable URI to parse about blank, the host field will be nil. But the help center site custom domain field in Intercom's data model is nullable because not all of our customers use custom domains. The risk here isn't obvious at all when you're writing the code and when you're writing specs for it. But when you call that line, the help center site find by custom domain uri.host with nil, because you've got about blank as the referrer, you just get the first row in the database that doesn't have a custom domain set, regardless of what you actually intended to look up. In the second example, this is kind of even more insidious because it depends on some custom Intercom implementation. But conversation.id is not unique, even though it is an active record model. We have a sharded database for all of our very high cardinality data, like our customer conversations. And in that database, the primary key columns are only unique per customer. To complicate matters even more, it used to be a normal active record model, and it was unique in the past. So to do the right thing here, you have to be aware of all of this context inside of Intercom. But since that cache key is not unique, that we're just using the conversation ID part, you could get a cache hit and read data that really doesn't refer to the object you're holding at all. And that could be a big problem. And this really highlights the risk of subverting expectations like this. So this is a standard Rails convention that decisions we made subverted, and we have to carry that cost. And that cost then falls onto engineers. Whenever they're building on it, they have to do all of this extra work, carry this extra cognitive load to make sure they get things right. So what were we doing to handle this? Like, how were we mitigating these problems? Honestly, our teams are just relying on best practices and tribal knowledge. We're having to do manual QA and often relying on security researchers in our bug bounty program to find issues like this. There was just a lack of systems thinking, and all of this was slowing down teams all over the place. Particularly, we were seeing problems when we were building entirely new features, expanding existing features, changing things that was slightly safer just by virtue of what we were doing. So now, how are we going to improve this? How do we get some systems thinking involved? Just going to need to take another step back and have some more background first. I'm actually going to give you a crash course in Intercom's data model, just so you understand that we can keep up to date. So internally, we call customer workspaces apps. So apps would be our internal name for customers. And the majority of our database tables have an app ID column that points back to the apps table. But those database tables are spread across many database clusters. So we have, I think, 10 MySQL clusters. Normally, I would be able to remember this off the top of my head, no problem. But up here, I'm struggling. And we have lots of places where these models are being looked up directly and not through an association on the app model. A long time ago, we did enforce querying for associations, but that just wasn't scaling for us. It was another thing that was keeping people slow. So we have places where we're just looking up by primary key, for example, or making queries on the fly. Secondly, users of Intercom are called admins. So if you sign into Intercom's web app and you're clicking around in the inbox, you are an admin. Admins are crucially not associated with a single app. So when I said that most tables in our database have an app ID column, admins are not one of them. And authentication of requests is happening on a per admin basis. And you can switch between multiple apps at any point during your session. So that all leads us to the problem we were having. And this is a direct quote from the scoping doc that we wrote and shared about this. So here we go. App X should never be allowed to access, meaning create, read, update, or delete app-wise private data. We currently have no automated protection against this, and we rely on engineering best practices to separate customer data. So that does a pretty good job of summing up everything I've said so far. Digging into that a bit more, private data can mean quite a lot of things. When we're trying to scope this full solution, we have MySQL, Elasticsearch, Memcache, DynamoDB, S3, lots of different types of data, lots of use cases. And in all of those different data stores, different access patterns to consider. For example, using ActiveRecord, you could be calling pluck to pull only certain database columns from the table and not actually instantiate your model object. Or you could be using select to pull certain columns and instantiate it, or just reading the full object in one go. We basically needed to go back and review all of the issues we'd ever had in this area to try and understand what kind of problems were we having in practice, because trying to bite off everything in one go was just too much. As we did that exercise, we came up with this table. So priority number 1 was just straight loading ActiveRecord objects from MySQL. Priority number 2 was reading and writing data in Memcache with Rails.cache, kind of more unstructured data. Number 3 was writing to MySQL of ActiveRecord, which seems like it should be important, but wasn't leading to as many issues in practice as the reads were. Number 4, only reading some columns of ActiveRecord, so this is the kind of pluck and select cases. And then as a kind of lower priority, like all of the other data stores like Dynamo, Elasticsearch, S3 that I mentioned. So this is kind of everything that we would need to solve for the ideal solution. based on what covered the most surface area in our application and the highest risk based on previous issues. But having done all of that, sorry, I was one behind. Having done all of that, we just cut scope aggressively and realized we could pull out the bottom 3 things and just cover loading active record objects from MySQL and reading and writing data from the cache, and actually solve basically every issue we had seen to date. So the guiding principle was simple. If we can identify something potentially dangerous and read an exception, we could turn a high-risk security incident into a simple availability incident. And we have practice handling availability incidents, dealing with exceptions, and so on, and the stakes are lower. So that's already a big win. So what did this solution look like? And the first thing we realized is that really, like, context here is key. The first step of blocking reads to the wrong app's data was going to be to define the right app. As we mentioned earlier, our authentication process only tells us about the right admin, but that isn't enough to know the right app. We need to decide what the right app is in the request and then save that context somewhere. So we're assuming a very simple world where every request has a single app that is the right app, and that we can work it out without loading anything from the database, which is a little optimistic, but it's a good abstraction to start with. So to do that, we just take the app object and we store it in a thread local variable and hid all of that behind a wrapper. So it looked like this in code, a simple block that we passed an app to, and inside of that block, the safe app would be set. So in principle, this is a solution, but rolling it out everywhere was going to be a tricky exercise. We had to basically find all of the edge cases, and that's hard. Like in an app our size and like over a decade of development, you realize it's basically all edge. So if you add like what we did to like drive them down was to add an after initialize callback to application record. And whenever a model gets initiated, check if the safe app is set, and if it is, compare the app ID on the safe app to the model's app ID attribute. If there was no safe app set, we could emit a metric. And if there was a safe app set and it doesn't match, emit another metric. This approach kind of let us start shipping it, rolling it out in a way that wasn't disruptive to engineers. So now we have those metrics, we just need to drive them to 0. So this is an example of a kind of graph from Datadog that I was sharing with my team every few days for several months. In this case, we're showing the number of active record objects instantiated where no safe app is set per 5 minutes. And I don't know if you can see, but the y-axis here, the laser's not working, but the y-axis up there shows we were instantiating about 1 billion objects every 5 minutes, or 12 billion per hour. And then at around 2:30, I shipped a change that cut that down by about 90%. And that process, kind of that order of magnitude reduction, kept going and going and going until eventually we got close to 0. As I said, like over a decade of development had resulted in a lot of edge cases. We fixed them where we could. So there might be like, oh, in this particular controller, it works a bit differently, or we have to get the safe app by going through this other model, whatever it is. Or if it wasn't possible, we had to exclude them. That exclusion process is actually like quite an interesting exercise. We were documenting all of the places in the app where like, oh, this particular controller, it's just not possible to load whatever object safely. And that kind of thing, every app is going to have those edge cases. We had never formalized them before, so one of the outputs of all of this work was a in-code documentation of every place where we weren't really obeying our own data modeling. This whole exercise, like I don't want to bury the lead, it literally took hundreds of PRs. I read pretty much the entire Rails code base in Intercom over the course of a few months. And it's, yeah, like I've got the example here. So this is only the PRs I remember to tag. We have over 400 PRs, just adding in all of these edge cases, fixing bugs, fixing things I'd found. It was a really fun exercise. And what we learned was, like, in basically every web request, we had some way of inferring it. So whether it was from the URL, headers on the request, from earlier authentication, like the session, whatever it might be, we also run a lot of async jobs, though. So most of those jobs start from web requests, and we just built in some middleware that propagates the state through all of the async jobs. So if you enqueue a job while the safe app is set, we write some additional metadata into the SQS message in our case. And then when that job is processed on the other side, we set the safe app again. All of that's happening invisibly to engineers. And the jobs that don't start from web requests, this is things like scheduled jobs, some other cases, we just had to go through them manually and make a call what the right thing to do was, kind of like the edge cases I discussed earlier. And all of this was done invisibly to engineers building our product. We didn't push this out onto teams saying like, hey, you've got to go through, look at your controllers, make sure you do the right thing here. We did all of this work like in the background. Eventually, this process got us close to 100% coverage. So that callback that was emitting the metrics could then be repurposed to raise an exception if we were initializing an object with the wrong app ID value. And that brings us to the point where one thing is down. We've covered that. We're raising exceptions if you're loading in a record from MySQL that has the wrong app ID. But we did mention we have to cover Rails cache too. One of the nice things was using ActiveRecord reads to explore the problem, check for coverage, ensured we covered pretty much everything, because basically all of our code paths use MySQL at least some of the time. So now that we have that context set everywhere, the solution was actually much easier. The challenging thing was not raising the exception, it was setting the context. So the Rails cache solution, you may not be aware, but when you read or write data into Rails cache without using the raw flag, it automatically gets boxed in an active support cache entry. We just modified the marshalling process for that to write in the safe apps ID into the entry object as an instance variable. That means that when we're unmarshalling the value later, we can check if it would check it and raise an exception if it doesn't match. So this is, again, making the assumption that every cache key contains data which belongs exclusively to the safe app. So if you write it, it can only be read by that app again later. That does seem like a pretty big assumption, but we're making an effort to be safe and secure by default here. So this property was true most of the time in our application, meaning the exceptional cases where we actually want to pass data between apps or use it for communication. They are the edge cases. And we have the same kind of process we did before, where we have another exclusion list that's based on cache key prefixes, meaning that you can opt out of these protections if you have an explanation for why. So yeah, that solves the problem. That's all of the scope we originally decided we were going to cover. And because we didn't have to do that context setting exercise again for Rails cache, we were able to ship it in a matter of days rather than in a matter of months, like for the ActiveRecord solution. But once we'd done all of that and we'd set this additional layer of context so we could attribute requests to a single app, we realized you can do some interesting stuff with this that's not necessarily related to these protections. So we thought, what else can we do? One thing we were able to do was start tagging all of our traces. We use Honeycomb for tracing, and you could quickly see what kind of experience a single customer is having now as a result of this. This was not the goal we set out to solve when we started on this work, but it's a great extra benefit, and it would have probably be seen to be too hard to do on its own without the additional value. We could use it to work out roughly how much compute time or resources each customer is using and figure out if they were profitable. We could use that to inform some business decisions in ways that we weren't able to before. I mentioned we have a sharded database. Before this work, engineers were having to, whenever they were talking to a different shard, put in a block routing the query to where they wanted it to go. Now we could do all of that routing automatically because we know what shard each customer resides in. And we were able to use it as a kill switch to shut down web requests or async jobs for just one customer in an emergency if we want to do something like that. There's lots of other ways in which we could use it. I've not been able to think of all of them here, but it's definitely a useful property. It's kind of maybe the most important thing I would like you to take away from this was the really interesting work was formalizing all of the assumptions we'd made about our data modeling over time. Things that, like organic decisions that had just grown up, we were now like, all of this was encoded in our app, and we were able to use that extra context for making lots of like cool improvements. So thanks very much. I feel like I'm a little under time, but great. Yeah, that's me. Thank you.